Welcome to Ashcroft's video on RTDs and thermocouple basics. I'm Dave Dlugos, Product Marketing Leader for the electronic temperature instruments. I've been with Ashcroft for 17 years and have 40 years of experience with temperature and pressure measurement, performing design, engineering, and product management. The agenda for today is RTD basics, thermocouple basics. Should you use an RTD or thermocouple? Ashcroft's temperature sensor models, the direct mount S50, the remote mount S80 and 81, temperature transmitters, and lastly, what's next? Let's start with RTD basics. RTDs are resistance temperature detector types. The most common RTDs are the 100 ohm platinum, which is used for most general industrial temperature applications. The RTD resistance is 100 ohms at 0 degrees C. The 1000 ohm platinum, which is used in low power applications, the RTD resistance is 1000 ohms at 0 degrees C. The reasons we use platinum are superior corrosion resistance, excellent long-term stability, measures temperatures over a wide range of minus 200 to plus 850 degrees. The most common coefficients are the 385 curve. Other RTD types, like nickel or copper, are used in limited applications. RTD probes are made to meet IEC standards. The sheath material is 316 stainless steel. The RTD probes have a high insulation resistance of 500 megohms at 250 volts. Standard sheath diameters are 1/8, 3/16, and 1/4. There are direct mount style probes. The RTD sensor is at the tip of the probe. They use minerally insulated cables or MI cables. They have a customer-specified type of lag. The most common lag is the shown nipple-union nipple lag. They have an electrical junction box or head directly mounted on the probe. There are also remote mount probe styles. The RTD sensor is at the tip of the probe. They use MI cables. They have a transition piece to connect the MI cable wires to the extension wire cable. The wire cable can come in a variety of wire insulation types and can have flex armor for additional protection. There are two types of RTDs, wire wound and thin film. Wire wound are a wound coil of platinum wire. They have a wide operating temperature range of minus 200 to 850 degrees C. Thin film is made with a platinum resistance pattern on a ceramic substrate with a narrower temperature range of minus 50 to 400 degrees C. The accuracy class of RTD is depending on the type of RTD and the temperature range being measured. Class B is good accuracy, plus or minus 0.3 degrees C over the widest temperature range. Class A is a better accuracy at plus or minus 0.15 degrees C over a narrower temperature range, and Class AA is the best accuracy, plus or minus 0.1 degrees C over a very narrower temperature range. To better understand the relationship of accuracy to temperature range, an example for a wire wound RTD rated Class AA would have an accuracy of plus or minus 0.1 degrees C from minus 50 to 250 degrees C, plus or minus 0.15 degrees C from minus 100 to minus 51, and from 251 to 450 degrees C, plus or minus 0.3 from minus 196 degrees C to minus 101, and from 451 to 600 degrees C. RTD wiring. RTD sensors are passive components that require an excitation current to produce an output signal. The resistance of the wiring used can add significant errors. There are three wiring methods: 2-wire, 3-wire, and 4-wire. 2-wire method, the resistance of the lead wire is added to the RTD resistance, and this could possibly be a significant error. 2-wire is typically used with very short cable lengths to minimize potential error. 3-wire method is better. If the 3 wires are all the same length, you can cancel out the lead wire resistance in the bridge circuit. 3-wire is the most common and is the method typically used with transmitters. 4-wire method is the best and is used for test and measurement applications. Next up is thermocouple basics. Back in 1821, Thomas Johann Seebeck described an effect that a low current flows when two conductors of different metals are linked and subject to a temperature difference. The two conductors connected to one another are termed a thermocouple. In this example, we have a welded thermocouple junction that is heated to 100 degrees C. This is termed the hot junction. If we lower the temperature at the other end of the thermocouple wires, termed the cold junction, to 0 degrees C, we have a temperature difference of 100 degrees C, which for this K thermocouple will produce a 4.096 millivolt signal. The cold junction is normally referenced to 0 degrees C. This is referred to a cold junction compensation. This is done by the circuitry in the temperature transmitter or PLC with the thermocouple input. Thermocouple construction. Thermocouple probes are made to ASTM standards. Sheath materials are 316 stainless steel or Inconel 600. They have a high insulation resistance of 1,000 megohms at 500 volts. There are direct mount probes. The thermocouple sensor is at the tip of the probe. They use minerally insulated or MI cables. They have a customer specified lag. The most common shown is the nipple union nipple lag. They have an electrical junction box or head directly mounted on the probe. There are also remote mount probe styles. The thermocouple sensor is at the tip of the probe. They use MI cables. They have a transition piece to connect the MI cables to the extension wire cable. The wire cable can come in a variety of wire insulation types, and they can have flex armor for additional protection. There are two types of junctions, grounded and ungrounded. Grounded junctions have the junction welded to the probe tip. Ungrounded is the most common, with the junction isolated from the probe tip. There are 8 thermocouple types that are used in different applications. Type T is typically used for cryogenic and freezer applications. Type J is used in many general industrial applications. Type E is used for higher accuracy measurement. Type K is the most commonly used thermocouple for general industrial applications. Type N is used in applications that need better oxidation resistance and less drift. Type S is used for high-temperature furnaces. Type R is used for high-temperature heat treating in biotech applications. Type B is the highest temperature thermocouple. Thermocouple types vary in the usable temperature range and cost. Higher temperature ranges equal higher cost, like the S, R, and B thermocouples. Next is the pros and cons of RTD and thermocouples. RTD probes are higher accuracy than thermocouples, better repeatability. They do not need cold junction compensation, better long-term stability. They are less susceptible to electrical noise, and they typically fail open, which can easily be detected. The cons are lower maximum temperature limits. They are less rugged than thermocouples. They have a slower response time. They do need a current source to have an output. They cost more than thermocouples. Thermocouple pros and cons. The pros are very rugged design. They have a fast response time, especially grounded junctions. A very wide temperature range. They can be very compact. They are tip sensitive. They are self-powered. The cons are thermocouples are less stable than RTDs. They may not fail open. Often they will drift out of specification. They are nonlinear. They need a cold junction reference. They have a small millivolt output signal. You must use compensated lead wire to connect them to transmitters. The accuracy of them degrades over time. Next is the Ashcroft temperature sensor models. S50 direct mount probes with either RTD or thermocouple sensors. They can have an explosion-proof or intrinsically safe approvals. They are normally made with NPT connections and used with thermowells. S80 remote mount thermocouple probes. S81 remote mount RTD probes. The S50 direct mount probes can have RTD or thermocouple sensors. The standard sheath diameters are 1/8 inch, 3/16, and quarter, and there are several millimeter sizes available. We offer 100 or 1,000 ohm RTDs, single or dual. We offer thermocouple types, K, J, T, N, and E, again, single or dual. The probes can have FM, ATEX, or IECEX approvals for intrinsically safe, non-incentive, and explosion-proof. The probe are fully certified as an assembly. They come in watertight or explosion-proof configurations with several head types available to meet many applications. We have many lag configurations. The lag length can be customized as well as the probe length. There are two basic design configurations for S50 probes, a DIN mount or spring-loaded mount. Both designs make sure the probe tip is held in contact with the thermowell tip for best heat transfer and vibration resistance. DIN mount probes use a terminal block attached to a DIN plate with two springs and screws. The screws thread into the head and the springs allow the DIN plate to move up and down when inserted in the thermowell. The spring will hold the probe against the tip. Spring-loaded mount probes use a spring-loaded fitting, which attaches to the probe and threads into the head. The terminal block is also screwed into the head. When inserted into a thermowell, the spring in the fitting will hold the probe against the tip. S80 and 81 remote mount sensors. Remote mount sensors have their electrical connection head remotely mounted from the probe by an extension cable. The extension cable can be protected by encasing in flex armor. Remote mount benefits are reduced weight. They isolate the electrical connection head from vibration and heat. Display transmitters can be mounted for easy viewing. Remote mounts are more accessible, and it's easy to adjust the head location and mounting. The image depicts two remote mount sensors, one with a standard head and the other with a display transmitter, connected to the probe with an extension cable. The probe is mounted in thermowell using a compression-style fitting. S80 remote mount thermocouple probes. Common sheath diameters are 1/8, 3/16, and 1/4 inches, 6 and 8 millimeter sizes. S80s offer K, J, T, N, and E thermocouple types. They are available with optional flex armor and remote heads. For approvals, we offer FM, ATEX, IECEX, intrinsically safe, and non-incentive approvals. The images show how the probe length and cable lengths are measured. If we install a spring-loaded fitting, like the image on the right, the L length is defined from the bottom of the threads to the tip of the probe. S81 remote mount RTD probes. Common sheath diameters are 1/8, 3/16, 1/4, 6 and 8 millimeter sizes. S81s offer the 100 and 1000 ohm RTDs. They're available with optional flex armor and remote heads. For approvals, we offer FM, ATEX, and IECEX intrinsically safe and non-incentive approvals. The images show how the probe length and cable length are measured. If we install a spring-loaded fitting like the image on the right, the L length is defined from the bottom of the threads to the tip of the probe, the same as on the S80 probe. S80 and 81 probe options. For electrical connectors, we offer standard and miniature thermocouple connectors, connectors and round pins for RTDs. For other options, we offer flex armor, protective springs that go on the cable, and compression fittings. Temperature transmitters we offer puck-style transmitters, which mount directly in the head, field mount transmitters, which can be remote mounted on an S80 or 81 probe, or direct mounted on S50 probes. The transmitter features we offer are 1 or 2 sensor inputs, 4 to 20 milliamp outputs. Some models have HART output, Bluetooth, and I/O link options. We have FM or ATEX intrinsically safe approvals available, programming to customer requirements, and we also have calibration certificates available. What is next in our RTD and thermocouple video series? We are going to do an RTD thermocouple model selection example, starting with an ISA-style datasheet describing an application. We're going to show you how to determine part numbers for the thermowell, the temperature probe, and the transmitter, which will be needed to work in this application. Thank you for watching this video. For additional information on Ashcroft temperature products, please visit ashcroft.com.